Okay, today, guys, we're going to talk about intermolecular forces. But I wanted to start with what inter means. The inter part here in intermolecular forces means between. So we're talking about these forces that act between molecules. And please have your Chapter 9 guided notes out. You're supposed to write down the definition for intermolecular forces. Here it is. They are the forces of attraction between particles. Between particles. So right down here, I've got a picture of two water molecules. This is a water molecule right here. So this would be the hydrogen, this would be the hydrogen, and this is the oxygen. Okay, so this is one water molecule. Here's another one. Now, if you look at the polarity of a water molecule, let's write down the electronegativity values. For hydrogen, it's 2.1. This one's 2.1, and the oxygen is 3.5. Okay, 2.1, 2.1, and 3.5. Now, if you were to draw the dipole moment arrow, for this molecule, it's going to go toward the higher number here. That means these hydrogens are slightly positive. That's why they've got positive signs here. The oxygen in water is always going to be the slightly negative part of the molecule. Well, if you've got more than one water molecule here, there's these forces called intermolecular forces that act between water molecules. Well, the oxygen is going to be attracted to which part of the other molecule? The hydrogens. Why? Because they are positive. And remember, opposites attract. So this oxygen is going to want to be attracted to the hydrogens. That's what an intermolecular force is. It's a force of attraction between molecules. And with water, this is what causes water to have cohesive properties. Water likes to stick to itself. In fact, you can think of it just like a little molecular magnet. Okay? If you have magnets, you can have the negative side is going to be attracted to the positive side. Well, it's the same thing here. This oxygen is going to want to be attracted to the hydrogen of the other one, and it pulls them together. And so that's why when you look at like the window as it's raining, water isn't just run down, it sticks together as big water droplets. And water likes to stick to itself. So that's kind of what we're going to be talking about today. There's a lot of different types of intermolecular forces, and that's what we're going to talk about. Okay, in fact, there's three main types of intermolecular forces. So let's go through them. The first one is called Dipole-Dipole Forces. Dipole-Dipole Forces. The second one that we're going to learn about today is called hydrogen bonds. And then we'll finish up learning about the last one, which is called dispersion forces. A lot of chemistry textbooks will abbreviate intermolecular forces this way. They just say they're IMFs. Okay, so IMFs. Intermolecular forces. What we're going to do is go through each one of these individually and learn about them in more depth. So first we're going to learn about dipole-dipole, then hydrogen bonds, and then we'll finish up with dispersion forces. Okay, so please be following along in your notes. Let's go to the first one, which is dipole-dipole forces. You're supposed to write something about the definition here. Dipole-dipole forces are attractions between oppositely charged regions of polar molecules. They are attractions between oppositely charged regions of polar molecules. So let me see if I can explain it. This is a hydrogen chloride molecule. Hydrogen's electronegativity value is 2.1. Chlorine's is 3.0. Because chlorine has a higher electronegativity value, it pulls the electrons in this bond a little closer to it. And since electrons are negative, this side's slightly negative. That means this side's slightly positive. Well, if you have more than one hydrogen chloride molecule, if you had another one here, because this chlorine is slightly negative, it's going to be attracted to the slightly positive hydrogen on the other molecule. And so this dashed line here represents that attractive force between molecules, and it's called a dipole-dipole force. So why do they call it a dipole-dipole? It seems a little redundant to say it twice, doesn't it? Well, here's why. This molecule, hydrogen chloride, has a dipole. Di means two, and pole, opposite sides. And so this is a dipole, and this molecule over here has a dipole. So there's one of the dipoles, and there's another dipole, and it's the force of attraction between them. So we've all played with magnets before. If you had this, and remember the chlorine is slightly negative, let's say that was one molecule, and let's say you could grab hold of another molecule here, and you turned it so that it was like this. Okay, imagine you had these two molecules, and you brought them close together, and then you let go. What's going to happen here as you let go? Yeah, just like if you had two magnets that were held negative and negative side together, if you let them go, isn't one of them going to flip around really fast? So it's going to flip around, and it's going to look like this. Okay, so you will never see negative attracted to negative. The negative is going to be attracted to the positive. So it does play effect, or have an effect on how they align these molecules. Okay, let's do a practice problem on this. It says, for each of the following questions, show how a dipole-dipole force will affect how the molecules will align. I'll do this one with you, and I think there's a part A and part B on this. So let me do part A with you. It says draw 4 hydrogen bromide molecules together and show how they will align. Well, first of all, if you look at hydrogen bromide, here's its Lewis structure. Let's find out which side's slightly negative and which side's slightly positive. Hydrogen has an electronegativity value of 2.1. Bromine is slightly more at 2.8. So if you draw a dipole moment arrow, this bromine is going to be slightly negative, the hydrogen slightly positive. So if I was to draw 4 of them, let's do that. Okay, so there's 1. Now I've got to draw 3 more. What's going to be attracted to this bromine? Hydrogen. The hydrogen of the other molecule. Okay? And so it's going to look like that. This slightly negative bromine is going to be attracted to the slightly positive hydrogen. And you could form some branching structure here, or maybe it's just linear. Maybe they just keep going like this. Okay, so there's 3, and there's 4. Okay? And so this force of attraction between molecules, right here, here, and here, that's what's called a dipole-dipole force. Okay, so maybe we should draw arrows to where the dipole between molecules, right? So it's that force of attraction between them. Now on part B, I want you guys to do this one. But let me help you with its Lewis structure real fast. So here's what this molecule looks like. So what I would like you to do is go through, write in the electronegativity values, figure out which side's negative, which side's positive, and draw 4 of them. Show me how they would align. So if you're watching the video, please hit pause and try this real fast on your own before I show you how to do it. Okay, let's see how you guys did with this one. I don't have a lot of space at the bottom of my board here, but let me see if I can fit it in. So if you draw the first one, let's see, it's not letting me draw that H. Anyway, there's an H on the bottom there. and then the bromine here. Okay? The bromine is going to be slightly negative. It has a higher electronegativity value, and so this hydrogen is going to be slightly positive. Guys, what happened to the polarity here? It canceled out. This was 2.1 and this was 2.1, and there's really no polarity in this axis. So along here there is, though. The bromine has a higher electronegativity value, so it's negative. So if that's one of my molecules, my other one has to be lined up with the hydrogen right there. Okay, so there's 1 and 2. Now you just got to draw a couple more. Okay, there's 3. Just make sure that the bromine is by this hydrogen, and you've got it. Okay, and now my dipole-dipole forces are going to exist between the molecules. So right there. And again, you could have made a branching structure or some kind of a curved structure, but just make sure the bromine was by the hydrogen. All right, so that's dipole-dipole. Now let's go to the second one. The second intermolecular force that we're going to learn about is called hydrogen bonds. You're supposed to write down something here in the definition, so let's go over it. Hydrogen bonds is bonding between hydrogen. Obviously, the name has hydrogen in it, so you've got to have a hydrogen and a more electronegative neighboring atom, such as nitrogen, oxygen, and fluorine. Okay? So you've got to have a hydrogen, but it's also got to have either a nitrogen, an oxygen, or a fluorine. Now, when I was going through chemistry and I was learning this, I just remembered NOF. Okay? NOF right here, you're going to hear me say that a lot in this chapter. NOF stands for nitrogen, oxygen, or fluorine. Now, if you look at the periodic table, everyone get your periodic table and look at it. Where is nitrogen, oxygen, and fluorine? What do you notice about those 3 elements? They're right by each other, 7, 8, and 9. I would like you to make outline these 3 elements, nitrogen, oxygen, and fluorine. Outline it on your periodic table so that we can remember NOF. And then also outline hydrogen. So with hydrogen bonding, obviously you need a hydrogen. You need a hydrogen. But you've also got to have one of these, a nitrogen, an oxygen, or a fluorine. Now there's a lot of molecules around that experience hydrogen bonds. The most famous molecule on the planet, water, does hydrogen bonding. And also, the bases in your DNA, the base pairs are attracted to each other because of hydrogen bonding. So I'm going to show you that in the next couple of slides. Let me see if I can explain it. This is a water molecule. So water is H2O. So this is a hydrogen, and this would be our oxygen. Okay, this is another water molecule down here. Okay. Now, does water have a hydrogen? It does. Does it have one of these NOF elements? It does. It has oxygen. And so between the hydrogen and the oxygen of another molecule, you see this little dashed line? That's a force of attraction known as a hydrogen bond. And a lot of chemistry textbooks will abbreviate this, and they'll just write H bond. Because hydrogen symbol is H, that's a hydrogen bond. Okay, so if this is a water molecule, and this is a water molecule, you just got to make sure that when you draw them, that the negative part of one molecule is attracted to the positive side of the other molecule. Now, how do you figure out which side's negative and positive? Well, hydrogen's 2.1 in electronegativity, and oxygen is 3.5. Okay? So the arrow would come down and to the right and up and to the right. You can only draw one arrow, so it would look like this, which means this side's slightly positive, the oxygen side is slightly negative. So when you draw another water in there, you've got to make sure that the hydrogen and the oxygen are attracted to each other. And that's what's forming your hydrogen bond. All right, let's see hydrogen bonding in DNA. You guys remember biology? A little bit? Your DNA is it single-stranded or double-stranded? It's double-stranded. Good. This would be one strand right here, and this would be another strand. Well, what holds the two strands together? Yeah, it's actually hydrogen bondings. Hydrogen bonds that occur between the base pairs. Do you guys remember the 4 base pairs in DNA? AT. So there's A, there's T, there's C, and there's G. What bonds with A? A T. So the other strand, this would be a T. If this strand has a T, what is the other strand going to have right here? An A. What's going to be bonded with the C? The G. And the G is bonded with the C. And so what is holding these two strands together is hydrogen bonds. Let me see if I can point them out. So this is adenine, which is an A, and this is thymine, which is a T. What is holding the two strands together is the hydrogen bonds here. Is there a hydrogen? Is there a NOF element? Yeah, there's nitrogen. Hydrogen, is there a NOF element? Yeah, oxygen. So this is a hydrogen bond, this is a hydrogen bond. How many between A and T? How many hydrogen bonds here? There's 2. Okay. Now let's look at G, which is guanine, and C, which is cytosine. How many hydrogen bonds here?
3.
There's 3. So if you get a segment of DNA that has a high CG content, there's 3 hydrogen bonds here. C and G like to hold together tighter. So it's more difficult to separate the strands of DNA if they have a lot of CG bases in them. So anyway, kind of interesting. I thought I would show you that. Okay, practice problem 11. Let's see if you guys can do this. It says draw 4 water molecules and show how they would hydrogen bond together. So I want to see how they were going to align and how they would form hydrogen bonds between them. So let me see if I can give you a few minutes to do this. If you're watching the video, please hit pause and try it on your own first. Okay, let's see how you guys did. First of all, let's draw 1 water molecule. Its Lewis structure, it's a bent, right? We should always remember that water is bent. If we draw in our lone pairs as well, that's a little more accurate. Okay, this hydrogen is 2.1, oxygen is 3.0, or is it 3.5? It's 3.5, sorry. This is a 5. And this hydrogen is 2.1. And so there's going to be a dipole moment arrow that looks like this. That means the hydrogens are slightly positive, this oxygen is slightly negative. So when you draw 4 of them together, you need to remember that. So if this is one of them, if we're going to draw another water molecule, you just got to make sure that by the hydrogen, there's an oxygen. And you can take this in any direction you want to go. I don't know, let's go this way. But water's bent, so we make sure to draw it bent. And then you can kind of just take it wherever you want to go. I don't know. But I think I've got 1, 2, 3, and 4. Okay? And I want you to label the H bonds, the hydrogen bonds here. So there's one there. This would be a hydrogen bond, and this would be a hydrogen bond. Okay, very good. How many of you guys got that right? Okay, I'm not concerned about the shape that you drew. Again, it can be branching, it can be linear, however you want to take those oxygens or those water molecules. All right, let's go on. Let's learn about the last type of intermolecular force, which is called dispersion forces. Okay? In your book, you're supposed to write down something here with the definition, but dispersion forces are very weak. They're the weakest of the intermolecular forces, and they result from temporary shifts in the density of electrons in the electron cloud. We've got a great animation that will demonstrate this in a second. But for right now, they're weak forces. They result in temporary shifts of electrons in electron clouds. Okay, now dispersion forces occur with nonpolar molecules. Okay. And remember from the last lesson, in order to be nonpolar, remember SNAP?
Yes, it had to be symmetrical.
In order to be nonpolar, it had to be symmetrical. And in order for it to be symmetrical, it's got to be symmetrical on every axis. So an example of this would be oxygen. Okay, if I draw oxygen's Lewis structure, it looks like this. So you guys tell me, is it symmetrical left and right along this axis? Yeah, it is. What about this axis? It is. So it is symmetrical, so it's nonpolar. If it's nonpolar, we know that the intermolecular forces acting on it are dispersion forces. Very weak. Very weak. In fact, that's why oxygen, here, this molecule, it's a gas at room temperature. There's not a very strong force of attraction between oxygen molecules. Another class of molecules that experience dispersion forces are known as hydrocarbons. So I wanted to talk about them a lot in the next few minutes. Hydrocarbons. Let's break down this word here. Hydro is for which element, do you think? Hydrogen. And carbons are obviously for carbon. So these are a class of molecules that are made up of carbon, hydrogen. Now the ratios change between carbons and hydrogens, but they just have carbon and hydrogen in it. These are a very important class of molecules because we get energy from hydrocarbons. This right here is methane. It's the main component of natural gas, which we use to heat our houses with. It goes up in even very large molecules like this one. Does anybody know what this molecule is called? Octane, yeah. And what do we use octane for? Gasoline, yeah. It goes in your gasoline in your car or truck, and that's how we power our cars. So, very important in terms of energy, this class of molecules. So here's the deal. Okay, this is kind of important. With dispersion forces, the strength of the dispersion forces increases with the size of the molecule. So these forces increase with the size of the molecule. So let me see if you got this down. I'm going to label this molecule A, and octane is B. Which one is going to experience more dispersion forces, A or B? B. How come? You're right. Why?
Larger.
It's larger. The larger they get, the more dispersion forces, the larger that becomes as well. Okay. Now this is a quick animation. It's showing, and I have to keep restarting it. But you see these black dots that are flying around everywhere? That's supposed to be the electrons. Okay, this is H2. Okay? And so each hydrogen has one electron. But notice, the electron cloud is now like this. Okay? And so those electrons are free to move about the whole cloud. Is there a moment in time where the electrons are both on one side? There could be, right? And then that would make it more negative. And the opposite side, where there's no electrons, is obviously going to be positive. I think this is a lot better animation here. But draw your attention to this one, okay, to this molecule. Now notice, when both of the electrons are on this side of the molecule, what pops up right here? A negative sign. Okay, well, if both electrons are on this side, what does that make this side by process of elimination? It becomes positive. This is what the temporary shifts in electron density in the electron cloud. Notice when this side becomes negative and this molecule next to it is experiencing a positive charge right there, what happens?
You go together.
They get closer together. There's opposites attract. So that's what dispersion forces are, is these temporary forces of attraction that exist when the electrons are arranged in that way. Now, does it happen forever? No, it's very quick, and it doesn't last very long. And so that's why they're pretty weak relative to the other two. Dipole-dipole is a lot stronger, and so is hydrogen bonding. But this does produce some force of attraction there, just because of where the electrons are in the molecule, or in the electron cloud. Okay. Okay, this is an important graph. I want to spend some time going over it. How many of you guys have taken the ACT? A few of you? So the ACT has just graph after graph in the science section. And the biggest piece of advice I could give you when you're doing questions on the ACT with the graphs is I would look at what the graph is reporting on the axes. Okay, so there's a y-axis, there's an x-axis. What's being reported on this y-axis, guys? Boiling points. Okay, so you start, these are temperatures. It's temperature. What's being reported on the x-axis? Molecular weight. So this is basically the size of the molecule, right? Well, and then we look at what's graphed here. We've got CH4 all the way up, and what's happening when we get up here? They're a lot bigger, right? So we can see this has a very low molecular weight. Octane, much higher. Now let's look at what's happening with the boiling points. If you were to draw a line here of best fit, what's the trend? As the molecule gets bigger, what's happening to the boiling point? It's going up. Okay? So that's the trend. Now let's figure out why. CH4 is a gas at room temperature. It's what comes out of the gas valves in our lab here. Methane. Okay? Octane exists as, what phase is it in room temperature? Liquid, yeah, you put it in the gasoline in your car. If we look at how the phases are organized, this would be a gas phase, this would be liquid, and this would be solid. If I was to draw the molecules in there, in a gas phase, they're very far apart. Okay? In a liquid, they're closer together. And in a solid, they are very close together. So you just got a bunch of them in a small amount of space. So let's try and figure out why this hydrocarbon, methane, is a gas at room temperature, and octane is a liquid at room temperature. What did we say about the dispersion forces? They get larger as the molecule gets bigger. So that means this one has more dispersion, right? More dispersion forces. Well, if you've got more force of attraction between the molecules, is that holding them together closer? Yes, and so because this is such a large molecule, there's more dispersion forces, these molecules are being pulled together closer, which keeps them as a liquid at room temperature. Now let's contrast that to what's happening here with methane. It's very small, not much in terms of dispersion forces are holding these molecules together, so they're allowed to spread out more. Well, when they're spread out more, that forms a gas at room temperature. And so, kind of an interesting graph. They're all hydrocarbons, but because of the size of the molecules, the dispersion forces can act on them in a different degrees. All right, practice problem number 12 kind of asks you about that. Okay, let's read it. Explain why methane, CH4, is a gas at room temperature and octane is a liquid at room temperature. Let me give you a second to think about that and write the answer down. So just write a few statements about the answer here. If you're watching the video, please try it on your own first. Okay, so I went ahead and wrote kind of what I hoped that you guys would have. There's just a couple of statements as to why this is happening. And I just put that CH4, because it's smaller, the dispersion forces are weaker. if there's not much dispersion force, these molecules are farther apart and it exists as a gas at room temperature. Now let's talk about octane. It's a larger molecule, so the dispersion forces are going to be stronger. That stronger dispersion forces hold the molecules closer together, and that makes it a liquid at room temperature because those molecules are closer together. So hopefully that kind of makes sense. Okay. I've got in your notes a place, and it wants you to list these intermolecular forces from weakest to strongest. And so what I've got is a slide up here that goes through how each one of them compare in terms of their strength. Now the weakest is going to be dispersion forces. They're the weakest. In the middle somewhere is dipole-dipole. And the strongest intermolecular forces is hydrogen bonding. So these are very weak. Dispersion. In the middle is dipole-dipole. Strongest, hydrogen bonding. Now I've got a quantified how strong these bonds were. So dispersion forces, if you see here, it takes 1 kilocalorie of energy in order to break that bond. How does that compare to dipole-dipole? How much stronger is a dipole-dipole force?
1 to 1.5.
Yeah, it's about twice as strong, isn't it? It's about twice as strong. This one takes 2 kilocalories. How much stronger is hydrogen bonding compared to dispersion? 12 to 16 times as strong. Yeah, it's a lot stronger. So hydrogen bonding is the strongest. Dipole-dipole is the middle. Dispersion are the weakest. And then what I did was I put an intramolecular force. We talked about covalent bonds a couple chapters ago. Look how much stronger covalent bonds are compared to intermolecular forces. So compared to a dispersion, compared to a covalent bond, how much stronger is a covalent bond? 400 times stronger than dispersion forces. So intra-ionic, covalent, and metallic are very strong. But in terms of intermolecular forces, hydrogen bonding is the strongest, dipole-dipole is middle, dispersion are very weak. Okay, now what we're gonna finish up this lesson talking about how to know, based on the structure of the molecule, how to know which type of intermolecular force is going to act on it. Okay, so there's a number of steps involved. The first step that you need to do is SNAP. Okay, SNAP is an acronym. What does it stand for, guys? Symmetrical is nonpolar. Asymmetrical is polar. Okay, so we're going to look at the Lewis structure, and you're going to go through the SNAP process right here to determine whether it's polar or nonpolar. Step number 2. If it's nonpolar, dispersion forces act on it. So if it's nonpolar, so it's symmetrical on every axis, and it's going to be nonpolar, dispersion forces act on it. Okay, step 3. If it's polar, so if it's asymmetrical, it's going to be polar. If it is polar, it could be hydrogen bonds, but it also could be dipole-dipole. So how can you determine which one it's going to be? If it's polar and it has hydrogen and one of the NOP elements, that's hydrogen bonds. But what if it's not? What if it has hydrogen but it doesn't have a NOP element? Then it's dipole-dipole. By process of elimination, it's going to be dipole-dipole. Let me give you an example of dipole-dipole. What about this molecule? Does it have a hydrogen in it?
Yes.
Yeah. But is chlorine one of the NOP elements?
No.
No. So it is polar. What kind of intermolecular forces would act on this one? Dipole-dipole. So there's one example. Okay, so what I've got now, guys, is some practice problems. We're going to go through a couple together, real slow. You're going to get the hang of this, and then by the end, hopefully you're able to do it on your own. So practice problem 13, let's go there. It says, draw the Lewis structure for the following molecule, then determine which type of intermolecular force would act on it. Okay, in this molecule on practice problem 13 is water, the most famous molecule ever. When you're drawing the Lewis structure, remember we have to total up the valence. How many valence from hydrogen? 1, but I got 2 of them, so there's 2 valence. And let's add that to the valence of oxygen. How many from oxygen? 6. So this molecule has a total of 8 valence electrons. Okay. Now the second step, which one goes in the middle? Does hydrogen ever go in the middle, guys? It doesn't. So let's put oxygen in the middle and draw its electrons. 6 dots. Remember, you just go clockwise around until you get to 6. Putting at maximum 2 on each side, max. So now that we've got oxygen's dot structure, where do you think those 2 hydrogens are going to go? Well, hydrogen brings 1 electron because it has 1 valence electron. It's going to go there. Can it be done? No, because these shared electrons are known as covalent bonds, and chemists will draw them as a line. Now with my lone pairs here, I still have to draw them. Okay? So there's water's Lewis structure. Now let's go through that process. First step said do snap. Guys, is this molecule symmetrical along this axis?
No.
It's not. What about this one?
No.
It's not. So this is an asymmetrical molecule, which means it is what? It's polar. Now with polar, it could either be hydrogen bonds or dipole-dipole. How can we differentiate the two? Is there a hydrogen? Is there a NOF element? There is. So water is held together by hydrogen bonds. Okay, so hydrogen bonds. Okay, let's try another one. Practice problem 14. I'll help you with the Lewis structure. Let's just draw it real fast. This one's pretty easy. Now what I would like you guys to do is go through the snap, determine whether it's nonpolar or polar, and then tell me what kind of intermolecular forces would hold these molecules together. So if you're watching the video, please try that first. Okay, let's see how you guys did. Is it symmetrical along this axis, guys? It is. It's a mirror image, right? What about along this axis? Yes, it's symmetrical. So it is symmetrical around every axis. That means it's what? It's nonpolar. What type of intermolecular forces act on nonpolar molecules? Dispersion. So hopefully you wrote dispersion. Dispersion forces. Are they very strong or are they weak? They're very weak. They're very weak. Okay, let's go to 15. You guys try this one. I'll help you with the Lewis structure. It's pretty easy on this one as well. Okay, go through the snap and tell me whether it's polar or nonpolar, and then what kind of intermolecular forces act on these molecules. Give it a shot. Okay, let's see how you guys did. First of all, let's do snap. Guys, is it symmetrical this way?
No.
It's not. So if it's not symmetrical, it's asymmetrical, which means it's what? It's polar. Now, with polar molecules, it can either be hydrogen bonds or dipole-dipole. Is there a hydrogen here?
Yes.
Yeah, but is there a NOF element?
No.
It's not. So what is it? Yeah, it's got to be a dipole. Okay. And those are, how are these in terms of strength? Strong, weak, or medium?
Medium.
They're very, medium, so they're in between. Okay, number 16. Let's do this molecule. You're breathing it right now. Oxygen, O2. Here's its Lewis structure. Okay, there's a double bond between the oxygens, and you got your lone pairs here. So now, guys, try it. You tell me what kind of intermolecular forces are acting on oxygen. Okay, let's do snap on this one. Guys, is it symmetrical along this axis? Is it a mirror image? It is. Is it a mirror image along this axis? It is. So it is symmetrical, which means it's nonpolar. What are the only forces that act on nonpolar molecules? Dispersion. Good. So dispersion forces. Weak, strong, or medium? Very weak. How many of you guys got it right? Okay, these are pretty easy, right? I think I've got one more for you. Practice problem 17. Practice problem 17 is on another famous molecule. This one's ammonia. So let me help you with the Lewis structure. And there's a lone pair there. Okay, so try this one. Tell me if it's hydrogen bonding, dipole-dipole, or dispersion. Okay, so let's do snap first. Guys, is it symmetrical about this axis?
Yeah.
It is. Yeah, that's a mirror image on both sides. What about this axis, though?
Nope.
It's not, because this hydrogen, there's not another hydrogen up here to be a mirror image with. And so it's asymmetrical, which means it's what? It's polar. It's polar. Well, polar can either be hydrogen bonding or dipole-dipole. Do we see a hydrogen? Yeah? Is there an off element?
Yes.
There is. And so this has got to be hydrogen bonding. Okay, in terms of strength, is it strong, weak, or medium? It's very strong, so this would experience very strong forces between them. All right. Okay, let's kind of wrap this up with some and summarize what we've learned about. Okay, hydrogen bonds explain why water is a liquid at room temperature. So water is a liquid at room temperature, while compounds of comparable mass are gases. Water experiences hydrogen bonds, which are very strong, so it pulls the molecules very close together, which keeps it as a liquid at room temperature. Here's a molecule that's pretty similar in size to water, methane. It's nonpolar, and nonpolar are held together by dispersion forces, which are very weak. And because they're very weak, they don't get pulled together very strongly, so it keeps it as a gas. And so that's why methane is a gas at room temperature. There's very weak forces holding it together. You have to write something here, I think. Ammonia is also very similar in terms of size to water. Ammonia and water both form hydrogen bonds, which are very strong. And oxygen is more electronegative than nitrogen, making OH bonds more polar and thus stronger. So because these guys have hydrogen bonding, holds them together tightly, it makes them liquid at room temperature. Okay. This table kind of summarizes that same point. Water compared to methane. Are they about the same size, guys, in terms of their mass? Yeah. But look at their boiling points. Much different here. Water boils at 100 degrees Celsius, 212 Fahrenheit. That's what it boils at. So that's when it goes from a liquid to a gas. Look at this one, though. Methane boils at negative 33.4. So at room temperature, what is methane? It's a gas. At room temperature, water is obviously a liquid. How come? What kind of intermolecular forces are holding water molecules together? Strong or weak? Very strong, and so it pulls these molecules together, keeps them as a liquid. What kind of intermolecular forces are acting on methane? Dispersion, yeah. Dispersion, which are very weak, so it's a gas at room temperature. Okay, here's a table that kind of reviews everything we just talked about, and I know it's a lot in this lesson. So you're supposed to fill this out in your guided notes. Let's go over it. Dispersion forces are weak. The electronegativity difference in the molecule is very small. Examples, hydrocarbons. Hydrocarbons are held together by dispersion forces. Dipole-dipole. They're medium in terms of strength. Examples, HCl, HBr are examples of molecules that are held together by dipole-dipole forces. And finally, hydrogen bonds. They're very strong. You have to have hydrogen, but you also have to have one of the NOF elements. So an example, water is held together by hydrogen bonds. So take a second there. You might have to hit pause on your video and finish filling this table out in your notes. Okay, so I hope you filled that out. I've just got one more slide, and I told you at the beginning of the lesson that the world is going to make more sense after this lesson. So let's see if it does make more sense. Okay, so I've got a picture here on this next slide of the world. 70% of our planet is covered in what molecule? Water. H2O. Okay? Now, if we just studied water and the intermolecular forces that hold it together, what type of intermolecular forces hold water together? Hydrogen bonds. Hydrogen bonds. Now, in terms of strength, are they weak, strong, or medium?
Strong.
They're the strongest. Okay, so they're very strong. And because of that, water molecules, because they're being held together very strongly, it holds them into the liquid phase. And so that's why water exists as a liquid at ordinary temperatures. Now, let's contrast that to some other famous molecules in our world. So in our atmosphere, okay, here's our atmosphere. We have a bunch of gases. What are some of the gases that are in our atmosphere that you're breathing in right now?
Nitrogen.
Okay, nitrogen. 70% of the air you're breathing is nitrogen. Now what I'm going to do is draw the Lewis structures for these molecules. Okay, so there's nitrogen, N2. What are some other ones?
Oxygen.
Oxygen, yeah, we better be getting oxygen. Okay, there's some hydrogen, H2. What else?
Methane.
Methane, okay, there is some methane. Here's what methane looks like. Now you should be noticing a common trend here with the gases. There's one more famous gas that I'd like to draw. Carbon dioxide. You exhale it every time you breathe out. So here's what carbon dioxide looks like. What do you notice? What's the trend with all of these gases in our atmosphere? Let's do SNAP, okay? S-N-A-P. Guys, are they all symmetrical?
Yeah.
In every axis, they are all symmetrical. So that tells us they are what? Nonpolar. What type of intermolecular forces act on nonpolar molecules? Dispersion. So these guys are dispersion. In terms of strength, weak, medium, or strong? They're very weak. And because of that, they're not held together very strongly. And so gas molecules are very spread apart. And they exist as a gas at ordinary temperatures. Does that make sense? Water is a liquid. These gases in our atmosphere exist as a gas. It has everything to do with intermolecular forces and how strong they are. So hopefully that makes sense. To finish up, guys, I've got a worksheet in the student workbook. It's called Intermolecular Forces Worksheet. So please go to your student workbook now. Again, it's called Intermolecular Forces Worksheet. Let's complete that. You should be able to do it by now. And hopefully this helped.